What is something that can only get bigger and never get smaller? You could say that almost anything you can think of, whether plants and animals on Earth or all kinds of celestial bodies in the universe, can be made smaller under sufficient external intervention. However, there is one thing that, even if you use the power of the entire universe, you could never make smaller. That thing is a black hole. This is related to a law proposed by Stephen Hawking, the Area Theorem. It states that the surface area of a black hole's event horizon never decreases. Whether a black hole swallows matter, or two black holes collide and merge, the final black hole's surface area can only increase or remain the same, but it will never decrease. What about Hawking radiation causing black holes to evaporate? That's a different level of the discussion. We'll come back to it at the end of the video. The black hole area theorem originated in the 1970s, from a brand new research field on black holes, black hole thermodynamics. It even has 4 laws that correspond directly to the 4 laws of classical thermodynamics. First is the zeroth law of thermodynamics. It states that, in thermal equilibrium, the temperature of a system is uniform everywhere. The zeroth law of black hole thermodynamics says that, for a stable black hole, the gravitational pull at every point on its event horizon is the same, meaning its surface gravity is constant. In other words, when Hawking radiation is ignored, the temperature of a black hole is its surface gravity. Next is the first law of thermodynamics. It tells us that energy cannot be created or destroyed. It can only be transformed from one form into another, and the total amount of energy remains conserved. In black hole thermodynamics, when a black hole absorbs matter or energy, its mass, angular momentum, and surface area all change accordingly. These changes are strictly constrained by equations, much like energy transformations in thermodynamics. In a certain sense, this can also be viewed as a form of conservation. The second law of thermodynamics is even more famous. It states that the entropy of an isolated system never decreases. The law of increasing entropy. Hawking was inspired by this law, and realized that the surface area of a black hole also never decreases. Isn't that a perfect match with entropy as a physical quantity? The difference is that a black hole's surface area is inversely related to its temperature. That is, as a black hole becomes larger, its temperature becomes lower, and its surface gravity becomes weaker. But no matter how small it gets, it never reaches zero. This leads directly to the third law. The third law of thermodynamics states that it is impossible to reduce a system's temperature to absolute zero through a finite number of steps. The black hole version says that a black hole's surface gravity can never be reduced to zero. This rule rules out the existence of extreme black holes with naked singularities. It is precisely these 4 laws that allow us to treat black holes, these extraordinary objects, as ordinary physical systems that obey thermodynamic rules. But here comes a problem. If black holes have temperature, then they should emit thermal radiation. Yet traditionally, black holes were thought of as monsters that only swallow and never emit anything. To resolve this contradiction, Hawking later proposed the famous Hawking radiation. But that's another topic. For now, let's return to the issue of black hole area. If we want to talk about black hole area, we first need to know how that area is actually calculated. Isn't a black hole just a sphere? Can't we simply use the surface area formula for a sphere? Yes. As long as we know the mass of a black hole, we can calculate its radius using the Schwarzschild radius formula. Then plug that into the surface area formula for a sphere. This gives us the surface area of a non-rotating, uncharged, static Schwarzschild black hole. However, real black holes are usually not static. They rotate. They are Kerr black holes. When a black hole rotates, its shape is no longer a perfect sphere, but an oblate spheroid, much like how Earth bulges slightly at the equator due to its rotation. For these flattened, rotating black holes, we must introduce a spin parameter. On top of the static case, the faster the spin, the smaller the black hole's surface area becomes. So the question is, how do we verify whether the area theorem is actually correct? Scientists came up with a clever idea: gravitational waves. Gravitational waves are ripples in spacetime. When 2 black holes merge, their immense gravitational disturbance creates ripples in the surrounding spacetime. These ripples are gravitational waves. By analyzing gravitational wave signals, we can infer the mass and spin of the black holes that produce them, and then calculate their surface areas using the equations. All we need to do is calculate the combined area of the 2 black holes before the merger, then calculate the area of the final black hole afterward, and compare the two. On September 14, 2015, the Gravitational Wave Observatory LIGO detected gravitational waves from a black hole merger for the first time. This was humanity's first direct observation of a black hole merger. By analyzing the signal, scientists found that it came from the merger of 2 stellar mass black holes. with masses of 36 and 29 times that of the Sun. They merged into a single black hole, with a mass of 62 solar masses. At this point, someone might ask, 36 plus 29 equals 65. Where did the missing 3 solar masses go? Simply put, they were released in the form of gravitational waves. But aren't black holes supposed to only swallow and never lose mass? How can their mass decrease? Here we need to clarify a concept. The mass we usually refer to for a black hole actually includes both its gravitational mass and the mass equivalent of its rotational kinetic energy. The former is the irreducible mass, the fundamental mass of the black hole. This is what only in, never out refers to. The latter comes from the black hole's angular momentum, energy converted into mass via mass-energy equivalence. The sum of these two is the total mass of the black hole. What gravitational waves carry away is not the irreducible mass, but the mass associated with rotational kinetic energy. Now back to the black hole area. Calculations showed that the combined area of the two black holes before the merger was about 235,000 square kilometers. After the merger, the new black hole's area was about 367,000 square kilometers. Clearly, the total black hole area increased. This was the first experimental verification of Hawking's black hole area theorem. However, the signal was not very clear. The signal-to-noise ratio was only 26. Although the increase in area could be seen, the precision was limited. Over the next decade, scientists continuously upgraded LIGO's equipment, greatly improving its sensitivity. On January 14, 2025, LIGO detected an exceptionally clear gravitational wave signal, with a signal-to-noise ratio as high as 80. The signal came from the merger of two black holes, 1.3 billion light-years away, with masses of 33.6 and 32.2 solar masses. They merged into a single black hole, with a mass of 63 solar masses. The area of the new black hole was clearly larger than the combined area of the two original ones. The confidence level of this result exceeded 4 sigma, reaching 99.999%. This is the most precise verification of the black hole area theorem to date. This research not only confirms Hawking's area theorem, but also provides a test of the black hole no-hair theorem. That is, a black hole can be completely described by just 3 fundamental quantities: mass, angular momentum, and electric charge. Of course, charge can be ignored for now, as it is generally believed that charged black holes do not exist in reality. Finally, let's return to the question from the beginning. If Hawking radiation causes black holes to slowly evaporate, doesn't that contradict the area theorem, which says the area never decreases? Not really. The area theorem belongs to classical general relativity, while Hawking radiation is a quantum effect. And even if a black hole does slowly shrink due to Hawking radiation, the second law of thermodynamics is still not violated. That's because, although the black hole's area decreases, the entropy carried away by the radiation outside the black hole increases. When you add them together, the total entropy still only increases. This is known as the generalized second law. So, looking back at the whole story, from Hawking proposing the area theorem in 1971, to LIGO's first gravitational wave detection in 2015, to the high-precision confirmation in 2025, there have been both technological breakthroughs and theoretical refinements along the way. Countless scientists contributed to this result. As technology continues to advance, we can expect even more and clearer signals to be detected in the future. Why does a black hole's area resemble thermodynamic entropy so closely? Are they fundamentally the same thing at a deeper level? Perhaps future research will give us the answers. See you next time. Bye.